Welcome back, everyone, or indeed welcome to Sussex University if this is your first. I'm going to give a very, very short introduction in which I try not to butcher Josh's academic history. But yeah, today we've got Josh who's going to be talking to us about neutrinos and all sorts of things that I avoid understanding in my research. But yeah, Josh did his PhD in Sheffield working with the Atlas experiment. He then moved to UCL for 3 years before moving to CERN. And then a very short period at Berkeley before coming here in 2022 to start a Royal Society University Research Fellowship. Yeah, a prestigious fellowship. Yeah, and without further ado, I'm just going to hand over to Josh.
Thank you very much, Will. Can everybody hear me okay? Is it coming through? I think it's coming through, isn't it? It's a real pleasure to be here. It's especially a real pleasure to see the room so full. So I'm going to try and tell you a little bit about some of the physics that we do here at Sussex in the physics department. It's particle physics stuff that we're doing, and I'm going to tell you about a slightly unusual experiment that we are involved in. So it's one of the newest experiments at the Large Hadron Collider at CERN. It's also one of the smallest experiments there. I'll tell you more about that in a minute. And we're looking for some of what I think are the weirdest particles that we know about, the strangest fundamental things that make up the building blocks of life, the universe, and everything, which are neutrinos. And if you look for one type of weird thing, it means that turns out you can quite easily look for another type. So we actually can use the same experiment to look for possible signs of dark matter. Okay, so I think people sometimes find particle physics really abstract and hard to get their head around. I'm going to try and really bring you along with me, taking inspiration from this thing, which is where there's a cartoon where a guy called Randall Munro tried to describe the Mars Curiosity rover using only the 1,000 most common words in the English language. So Mars rover turns into space car for the red world. Then you have things like there's a laser-based experiment that becomes thin burning light gun. The space talkers are the antennae. And I'm going to give you a bit more credit than that, but I'm going to try and really keep things as simple as I can as I go through. Okay, so the title of my talk was Catching Ghosts. And what the ghosts are these weird neutrino particles that are very hard to detect. There's 3 types of them, and I'll tell you all sorts of more information about that in a minute. And if there's something I'd like you to try and take away from today, it's 2 things really, which are that neutrinos are weird and very hard to detect. Despite that, they tell us an awful lot of interesting things about the universe, and actually might be related to lots of things that we don't know still about the universe. So I asked ChatGPT to tell me what neutrinos are weird and very hard to detect can be in the 1,000 most common words used in the English language. And it turns into tiny spirit things are odd and hard to catch. And these are the cuddly toy versions of these same neutrinos. You'll see this V symbol here, for everybody probably knows, but this is a nu sign, the Greek letter nu, and that's what we represent the neutrino with in particle physics. And then there are different flavours, these E, mu and tau, which I'll say a bit more about in a minute. Okay, so I said that these neutrinos are very weird, but they're actually one of the most abundant particles in the whole universe. If you ignore photons, light particles, then actually the most abundant particle in the whole universe. And they're so abundant that there's about hang on, how many is this? 1 trillion of them going through an area the size of your hand every second. Every second there's 1 trillion neutrinos going through an area the size of your hand. That's quite a lot, but obviously you don't feel them, you can't see them, there's no way that you can tell that they're even there. And that's one of the weird properties about neutrinos. They have a very low probability of interacting with other particles. They're very hard to detect, and that's why we need quite different types of detector technology to try and find them at all. So that hopefully sets the scene a little bit for what I want to tell you about in the next 45 minutes or so. But I always wanted to take a quick step back and go through what's the whole point of doing particle physics in general, and what are we trying to do as particle physicists. So the what, the why, and the how. So starting with the what. So what are we trying to do? Well, we're trying to understand the things that make up everything and why those things behave the way that they do. So, the very modest aim of trying to understand everything, which is, kind of hard, but we do our best. So sometimes it's not very easy to get your head around the big or the small numbers associated with fundamental particles. So here's one way of trying. So everything's made up of atoms. I guess probably everybody in the room already knew that. But there are more atoms in a single grain of sand than there are grains of sand in the whole world. So if you can try and get your head around that a little bit, maybe it gives you an idea of the small scales that we're looking at. And of course, the different types of atom give rise to the periodic table, all of the chemical elements, and then that describes all of chemistry, all of biology, all of life, all of everything. But it's all building on top of these smallest fundamental particles, the smallest bits of stuff that we think exist in the universe. An atom, as people will all know, has got a nucleus in the middle that's made up of protons and neutrons and an electron cloud around the outside. And those protons and neutrons, though, are not just fundamental particles themselves. They are made up of even smaller particles, which are known as quarks, which is the worst named particle ever, but fine. And so between these three particles, you can basically discuss most of everything that you see in day-to-day life. We tend to try and represent this picture of our best understanding of particles and their interactions and so on through something called the Standard Model. It's the best theory that we have for this, and people often like to present it in this kind of picture. So I start adding the pieces in. So I already said that the protons and neutrons are made up of quarks. In fact, they're made up of an up quark and a down quark. And then, of course, you have the electrons that orbit around the outside, and this is what makes up atoms. But every lepton, so an electron is a type of particle called a lepton, and they come kind of in pairs. So you have an electron and its partner neutrino, so an electron neutrino. And this is what we call maybe one family of particles with one generation, but there are actually multiple generations, and they're all kind of copies of each other. And basically the only difference is that they get heavier. So for instance, the electron has a heavier copy of itself called a muon, and that has its corresponding muon neutrino. And then the tau lepton is a heavier version still, and that has a corresponding tau neutrino. And then it's the same for the quarks, but we don't worry too much about those. And so that's, this little segment of this thing is what I'm going to try and tell you a bit more about today. And this is why you had these subscripts on the previous pictures where I showed you. So you have three different types of neutrino: an electron neutrino, a muon neutrino, and a tau neutrino. So that's all well and good, but those are just the particles here on the outside that all the stuff in the universe is made up of. It doesn't tell you anything about how they behave with each other, and that's described by the force-carrying particles. So this is the ones in the middle, in the blue. So you have four of these. You have the photon on the top left, which is responsible for the electromagnetic interaction, so light and magnetism. You have the gluon, the G, which is responsible for the strong force that keeps all of the protons and neutrons bound together inside the nuclei of atoms. And then, and then you have the W and the Z bosons, that are responsible for the weak force. And you have, again, very sort of exciting naming conventions: strong, weak, and that's because they are relatively both stronger and weaker than the electromagnetic force. Nobody said that particle physicists weren't anything if not imaginative. We don't talk about gravity. We leave that to the cosmologists and everybody else. It's so weak that we can't really do anything too much useful with it. The weak force is the one that's maybe most important for neutrinos, and one of the things that it describes is radioactivity, how the sun shines, all of this kind of thing. And it's other than that, you don't tend to sort of experience in any meaningful way in day-to-day life, but still it's an important part of this picture. And then the final piece of this picture is the Higgs boson, the particle that gives all of the other fundamental particles their mass. And, okay, so that was right, wasn't it? So you have all the particles, you have a set of rules. You don't need to know what this is, but this is the rule book for how all of these things interact with each other, how they're allowed to move, how they're allowed to do different things. It's obviously horrifically complicated. Somebody always jokes that there's a typo in here and you've got to spot it, but I've never found it myself. There's a wrong minus sign somewhere or something. You can condense it down into something the size of the mug. If you go and visit CERN, you can buy this from the gift shop over there. And then you can also buy something like this. So all games need rules, and the particle physics rules can actually be turned into a twister derivative that is also made by CERN, but I don't know if they sell this in the gift shop. Okay, so that's sort of what we're trying to do. I just want to say a few words about the why, although the why is kind of easy in a way, right? Because really the reason is because we're curious. People curious, as humanity, hopefully, we always try to understand what's going on around us a little better. So, I said already, what we're trying to understand, well, we're trying to understand you and me, the sun and the earth, the 100 million suns in 100 billion suns in our galaxy, and 100 billion galaxies in the visible universe. So, yeah, pretty modest, just want to understand everything. So how are we doing? We're doing all right. So, over 15 billion years of cosmic evolution, we can use some of the particle physics I just told you and a bunch of other physics to explain quite a lot of what happens and why the universe is the way that it is. But there are still quite a few things that we really, really don't understand, and that's kind of what's left as my job and my colleagues' job is to try and do a little bit better there. So, and it turns out there's quite a lot of what we don't understand connected to neutrinos, and this is partly because partly because I'm giving a talk about neutrinos, but partly because they're this particle that has quite strange properties and that was less well known maybe than others until more recently. Okay, so I already told you that neutrinos are weird. It also turns out that neutrinos are naughty. They already broke the rules of the game. I gave you this big, long equation, and in it doesn't say anything about these particles having any mass. So, a photon is massless. It travels through the vacuum of space completely unimpeded. It can go at the speed of light, the fastest that anything can go, because it has no mass. In the standard model, it's the same for the neutrinos, except for we measured them, and it turns out they do have some mass, albeit a very, very small one. So the rough scale of the neutrino mass is a millionth of the mass of an electron, which is, an electron's already very, very light in the scale of fundamental particles. And according to my notes, you'll have to read it out because it's hard to remember, it's 10 billion times smaller than a grain of sand, apparently. So that's how light the neutrinos are. Don't know if that's super useful, but there we are. And the thing is that the fact that these little guys here have some mass has an important consequence on their behaviour, what they're allowed to do as particles. And in particular, it means that they can change between flavours. So they can, what we call oscillate. So you can have an electron neutrino can travel through space, and if you had a neutrino gun and you send it a few hundred kilometres away, and then you measure it, there's a probability, a not negligible probability, that it will turn into a muon neutrino. Same for muon neutrino and tau neutrinos, and this is not really normal and is not what happens with most other fundamental particles, and it's a direct consequence of these things having mass. And the way that we kind of describe this in the end is by, when they're travelling, they stop being individual electron, muon and tau flavours, but they turn into mass states. They're almost mass flavours. So you can see this. Count the I's. So this is the M1, the mass 1, the mass 2, and the mass 3. And these are three different types of neutrinos. And when they're travelling, they're one of these three types. It's a bit like sort of a Schrodinger's cat type thing. Until you look in the box, you don't know which type they are. It's a weird outcome of quantum mechanics. And so, for instance, this M1 one is mostly made up of the electron neutrino, we think, but we don't know, and there's lots of measurements that still need to be done to understand these things better and how this mass generation comes to be. There's another interesting property of neutrinos that can help us understand a fundamental principle of the universe that we don't yet. So we live in a matter-dominated universe. That's kind of easy to know because there's stuff here. If in the early universe there was an equal amount of matter and antimatter, well, these two types of particle will just come together and annihilate with each other. And all they'll leave behind is photons. They'll just leave light. So the whole universe, so even if, you know, the same number of particles and antiparticles have been produced similar to what we'd expect, what we can see around us, but there was exactly the same number of particles and antiparticles, then we would not be here, there'd be nothing here, there'd just be a universe filled with light bouncing around, or I don't know what happens in the universe with only light in it. Maybe it doesn't bounce around. Travelling in very straight lines. And you don't need a big asymmetry in the amount of matter and antimatter. You need something like 1 part in a billion. So for every billion antimatter particles, you need 1,000,000,001 matter particles to get the observed amount of matter that we have now in the universe. But we don't know what creates that imbalance. We don't know where that comes from currently. But it turns out that neutrinos can maybe give us an answer. So when I talk about matter and antimatter, you can think of an electron. An electron has a negative charge. Its antiparticle, which is called a positron, has got a positive charge, and that's a kind of clear and obvious way to distinguish this matter particle and this antimatter particle. Antimatter and dark matter, by the way, completely different things. So I'll come back to that, but completely different things. But that's not true for a neutrino. The neutrino doesn't have an electric charge, it's neutral, and so if you say, oh, I'll just switch it to its antiparticle, what does that mean? There's then no longer a clear handle on what's the difference between those two particles. And so we're still trying to understand whether or not a neutrino is its own antiparticle or not. And the reason why it's interesting is because it could then generate this asymmetry. If you have one of your antimatter particles turning into a matter particle, and you should do the same thing again, all of the light is, most of the matter and antimatter particles all annihilate and just give you a load of light, but you do get this leftover bit of matter, and that's us. And so we'd kind of like to know how that happens. There's one final thing about neutrinos that I'm going to mention today that's kind of interesting. So I talked to you quite a lot about the fact that there's these 3 different types of a neutrino, but we actually have measurements of neutrinos that imply there might be a 4th. And this thing, if it existed, we call it a sterile neutrino, because if it was interacting in exactly the same way as the normal neutrinos, we would have seen it already. So it has to interact in a weird way, and the hypothesis is that this thing only interacts via gravity, not by the weak force, which is the main way that neutrinos interact with things. And that means that if it doesn't interact via the weak force, then it's very hard to detect experimentally, except for, because of the fact that neutrinos do these oscillations between different flavors, the existence of a 4th type changes the probability of those oscillations, and so you can do these kinds of measurements to try and work it out. Okay, so that's the why. That's why neutrinos are interesting in general. Okay, so the last bit is the how. So how do we try and measure these weird and wonderful particles? So I'd like to remind people again about the scales of things here. So it's hard to see fundamental particles full stop, right, because they are tiny. You can't look at them under a microscope. So the step in size from the entire observable universe to Brighton and Hove is the same as the step in size roughly of Brighton and Hove to fundamental particles, and so it gives you a sense for how small these things are. And that makes life difficult, but it's even worse because, like I mentioned to you before, if you try and catch these things, they just fly straight through your nets. They don't interact with the stuff that stops you the vast majority of the time. Luckily, they do sometimes get stuck in the nets. The problem is that this happens a 1/1,000,000% of the time, and so it's very difficult to see these things. And then, so that means that there's various things that you can then do to try and improve your chances of being able to see these particles. And one thing you can do is build a gigantic detector. So this thing's called the IceQ detector. Here is an Eiffel Tower for scale, because otherwise it's hard to get your head around it. It's roughly 1 kilometre across, and as you can see, nearly 3 kilometres deep. And the whole point here really is that the larger the thing is, the better chance you give yourself of a neutrino hitting something in it. And then it's got a whole bunch of measurement devices, and that's what you look for. Here's another pretty cool experiment called supernovae. This is humans for scale in a boat, in a rubber dinghy. One of the world's most precise particle physics experiments, and you still have some people in a rubber dinghy going around the bottom. So this thing's filled with water. All of the little gold circles here are, again, measurement devices. So what happens is if a neutrino comes in and it interacts with the water, it gives off a very characteristic sort of flash of light, and then you can measure that flash of light to try and understand the properties of what happens. So, again, to give you a bit of scale, these are to scale. They're not exactly the right shape, but this is the scale of IceQ. This is the scale of supernovae. So both pretty big. Even supernovae is pretty large. I said to you earlier that FASER, the experiment that I want to talk to you mostly about today, is the smallest experiment at the LHC. It's probably also one of the smallest neutrino detectors ever built. Can you see the pixel up here? That's nearly impossible to see. So we can zoom in a bit, and not really, still can't really see the pixel. If we zoom into to the supernovae now, you see this thing. And so this tiny detector has quite a complementary physics program to the other neutrino detectors, so it's not trying to do exactly the same thing, but it's a very different philosophy in how to look at neutrinos and trying to understand them better, which is quite a fun thing to work on, why it's a fun thing to talk to people about. For some reason, it's been described as the size of a few washing machines. I'm not sure that that's a standard unit, but okay, fine. It did come in some news article where somebody thought this was a good way of explaining what was going on. And then somebody else thought that this suitcase-sized neutrino thing was a good way. Well, I don't know. I'll lose the point. I mean, I think a tiny new experiment at the LHC is maybe a little bit easier for everybody. Okay, so I'm going to tell you in a second. I'm going to tell you a little bit about FASER and how it all works. But firstly, I wanted to see, show of hands, are there any Star Trek fans in the audience? Yeah, there's a few. So people got the reference. Yeah. No, that's the wrong one. FASER is the same name as the weapons in Star Trek. Somehow we also haven't been sued yet for the fonts. That is almost certainly illegal, but everybody seems okay with it up till now. And in one of the first publications, first papers that was ever written that proposed FASER, has this lovely line in it where it says, the acronym recalls another marvellous instrument that harnessed highly collimated particles and was used to explore strange new worlds. And that is basically what we do. And I'll tell you a bit more about it now. So I told you it was at the Large Hadron Collider at CERN. The yellow thing here is a Large Hadron Collider with the Alps and Mont Blanc even at the top in the middle for a sense of scale. You know, it's one of the largest and most complicated scientific experiments ever. It's you have particles going around at 99.99999% of the speed of light, around 11 million times a second. Lots of big numbers associated with it. And as part of this thing, you can see on the top right the ATLAS experiment. And as Will said in the introduction, I also work on the ATLAS experiment. And that's kind of the source of our neutrinos for FASER. There you have, again, one of the largest and most complex scientific experiments ever built. It's a 7,000-ton detector. It's 7 stories high. It's got 100 million electronic channels. It's a pretty big endeavour in general. But it turns out that within it, you produce an awful lot of neutrinos, and that's really the whole philosophy behind. Oh, it's really bright, isn't it? The whole philosophy behind FASER. So this is Atlas again with two standard size EU people for scale over here, so you can get an idea of how big it is. And traditionally, so Atlas has its own huge physics program, right? And what the general way that Atlas is looking for beyond the standard model physics, new physics to explain all the stuff that we don't understand, is traditionally looking for very high energy particles that are produced. So here the two LHC beams are coming in from the left and the right, and they collide right in the middle. And usually if you have something sort of interesting and a high energy collision, the products of that collision come out parallel to the plane of the collisions. And the types of new particles or exciting physics that you might see tend to be looking at numbers of events in the region of like hundreds and hundreds of thousands of collisions that you can try and single out to find this new physics that you're looking for. Well, that is a perfectly legitimate and a very good way of looking for new physics, but so far we didn't find any, and so it motivates exploring other avenues. And one other avenue that you can do is to exploit the fact that 100 to 100,000 is a tiny fraction of all of the collisions. Most of the collisions are kind of more glancing blows, and the two beams come in from each side, they have some kind of low energy interaction, and then they mostly pass past each other. And therefore all the particles produced in those collisions, just through conservation of momentum, also just go in what we call the very forward or very backwards directions. And there's, so here, I've got it written down, thank goodness. 100 trillion to 100 quadrillion particles, this is in the current data set that we have basically, get produced in these forward directions, in this very straight down toward, like in the same direction as the beam's going, more or less. And so, you can imagine that if you have quite a lot of neutrinos coming out of these collisions, even if your detector is small, if you put it in the right place and you throw enough neutrinos at it, a decent chunk of them will interact in your detector and you can try and measure them. And it's the same idea for the dark matter particles that we are also looking for, that I'll talk about later. So, and they're also much higher energy. So I talked before a bit about like the super Kamiokande. Those are lower energy on the whole, those neutrinos. The ice cube ones are higher energy, but then it means that it's complementary. We're in the middle. I'll say more about that in a minute. So this is what we did. We plonked a detector here. We looking for dark matter particles and neutrinos, and it turns out, through luck, pure blind luck, that there's an old tunnel. It's like CERN's supposed to be a very high-tech, cutting-edge facility. It turns out that if you stop needing a tunnel, it just sits there and gets dusty. So, and it turns out that if you take a straight line and you go from where the collisions happen in Atlas and just keep going, you firstly go through a bunch of the LHC magnets, which is fine. All of your backgrounds are charged particles and they get bent out of the way, but the neutrinos don't have a charge, so they just keep going straight. Then you go through about 100 meters of rock, which is also good because it blocks out potential other backgrounds, and then eventually you arrive at FASER. And you can do this very low background, very high-tech search for new physics. Now this is very dangerous. Actually, I'll kill the music. And this is just saying the same thing, basically, but in nice fancy CERN video. So this is the FASER detector. I'll tell you more about it in a second. And it's just sitting in this tunnel. This tunnel is going uphill over there. And what you're waiting for is for these collisions in Atlas. So this is the Atlas detector. The reason why the rate is so high is because you get 40 million collisions a second inside Atlas. And in some of those collisions, you get these neutrinos produced. And they're going to come out of Atlas going this way in a minute. Here we go. And they're going to travel in this straight line down the tunnel, and they're going to leave the tunnel, then go through the rock, and then they're going to come through a few meters of concrete, and then we can detect them inside this FASER detector, which I'll tell you how it works in a minute. And so, yeah, this is the whole point of it. That's the animation. This is how it looks in real life. So one thing you have to do is, if you want to build a detector that's the wrong side of the LHC, you have to build a bridge over it so you can carry the stuff, which gives you the nice opportunity to be able to stand on top of the LHC and look at it going down, and you can see the curvature of the magnets going around. This circuit, this ring is 27 kilometers long, so it curves very slowly. It's very hard to see normally when you're underground. And so in this, if I overlay what's happening, so you have Atlas on the right-hand side here, the particles are coming through and they're interacting in FASER, and it could be a neutrino, it could be some other long-lived particle. And this is proof that I did something useful with at least a short fraction of my time at CERN. This is me underground before we installed FASER, and the black sort of tunnel behind is where it ended up sitting. And this is the FASER detector. One important thing to note about all of this is hopefully got across that we had a disused tunnel that was sort of happened to be in the right place. The whole philosophy of FASER is to be kind of cheap and cheerful. It cost about $2 million in total to put together, which doesn't sound super cheap, but it's a lot less than all of the other things going on at CERN for the most part. And one way of doing that is beg, borrowing and stealing. So actually we have these calorimeters and tracking stations that were partly borrowed off two other experiments at the LHC, so LHCb and the Atlas experiment. They were literally leftover bits of kit, and we said, can we have them? Are you sure you don't need them? And they said, sure, go for it. So that was nice of them. So back to the 1,000 most common words in the English language. This is what these different things do. So your neutrino, or dark matter particle, or whatever, is coming in from the top right. And the first thing it gets to is the catch tiny spirits box. I should have put box. This is the neutrino detector part of FASER. Then it goes through these yellow things, which are remove the wrong type. So you don't want to, if you're expecting a particle that doesn't usually interact with anything to suddenly interact inside your detector, you expect to see nothing at the beginning of the particle going through, then it interacts, and then you see stuff afterwards. So you block out the stuff that doesn't interact by requiring that there's nothing in these yellow detectors at the front. Then you have to measure the position of the particles as the decay products of them. So they smash into it, they don't stay a neutrino, they produce other particles, and you can measure those other particles coming through. These are magnets, the blue things, and they're there to measure the charge of the particles going through. The orange things are trackers to measure the position, and the red things are to measure the energy. And in the end, the signature of a neutrino passing through this detector is very unique. It's quite easy to identify and separate out from everything else. And this is just the same thing, but in real life. And yeah, you saw it a bit already. Okay, so I'm half an hour in, and I just got to the start of the results, so hopefully that's okay. So what I want to tell you about is the fact that this experiment I just explained has, for the first time, observed colliders produced in neutrinos produced in a collider, which sounds surprising when I tell you how many neutrinos are produced in a collider. But this was just not an instrumented area. There's no detectors there. It wasn't really thought to be interesting physics. And what we've essentially learned over the last few years is that you can do an awful lot of interesting physics with these kinds of detectors. As I mentioned before, there are different types of neutrino measurements already. So if we look in this middle one, this is the muon neutrinos. And this big ice cube, this line at the top is the ice cube measurements, with that giant detector that's in Antarctica that I mentioned before. Down at the lower end, you have a load of accelerator experiments that are also measuring neutrinos, but you have nothing in between. And here is like a projection before we took any data of what FASER should be able to do. And you can see it's really nicely bridging this gap. So we're looking at much higher energy neutrinos than the accelerator data, lower energy than you get from ice cube, from neutrinos from much further outside the galaxy, and then you have a sufficient precision. The size of these bars is how large your uncertainty is on these measurements, that you can really say something interesting. So I said before that it's 1/1,000,000% of a chance of a neutrino actually stopping in your detector, roughly. And that comes from these numbers. So 10 to the 11 is a huge number of muon neutrinos that get to our FASER detector, and that we expect to see in the full amount of data taking that's still got a couple of years left to go. We expect to see around 1,200, something like that. And I said that the signature of these things is very sort of clear, and it's represented schematically with this diagram. So this time the neutrinos are coming in from the left-hand side of the board. This green thing is the bit where you say, actually, I don't want to see any sign of anything in my front of my detector because the neutrino shouldn't interact with that, partly because it's very light. This box is made out of tungsten. It's about 1 and a bit tons. It's very heavy, and that gives you a higher likelihood of the neutrinos interacting. So the first bit, you expect to see nothing, so you make sure there's no sign of any particles going through it. Then you look for the appearance of a bunch of the signatures of a neutrino interacting. And you measure those in your tracking stations. Then you have, for instance, in the case of a muon neutrino, you always produce a muon in these types of interactions, which is this thing that's a bit like an electron but heavier. And that thing goes all the way through your detector, and then you can measure the energy deposit, well, the small energy deposit that you expect in the calorimeter at the end. And there are backgrounds that you have to think about to make sure that you're not going to get some particle coming from Atlas that somehow makes it all the way through here and then scatters off the rock or something and comes at an angle and then just suddenly creates something that looks like a neutrino but isn't. But we spend a lot of time trying to do that, both using the data and using simulations. And we did this, and this is the result. So on the left-hand side, basically everything in this dashed line box is what should look neutrino-like. This is the momentum of the muon on the x-axis and how far away it is from the center of the detector on the y-axis. And you can see we have a big background, but it's not where we're looking, and we just look inside this box, and we see around 156, I think it is, 153 neutrino candidates in this box. Then we can look where they are, and you expect them to be more or less uniformly distributed. So the red cross here is if you drew a perfectly straight line all the way from Atlas into FASER. It doesn't quite go through the middle, but it just goes in at the bottom here. And then this is the distribution of all of those neutrinos, and they appear more or less in the place that you'd expect them to. And so this is the first ever detection of collider neutrinos, and this happened back in March earlier this year. And these are muon neutrinos, these ones. So this is quite exciting. And then in the summer, we've started a new analysis. So I didn't really talk about it yet, but that tungsten box at the front that's there for the neutrinos to give them the best chance of interacting, because it's very heavy, is actually a detector in itself. It's layers of tungsten with layers of what we call an emulsion film, which is basically like a photographic film, and it's very, very precise. And you can measure very precisely the details of the neutrino interaction, and you can kind of see here, I won't go through it, but they look quite different depending on what type of neutrino it is that's interacting. And there's a very complex, long procedure for developing and analysing the films. I mean, I really like photographic films. This is them all being developed in a room at CERN. And this is an example of an electron neutrino event. And it's kind of beautiful, mainly because of the colours, but also because it's a really clean, clear electron signature. So this is, on the left-hand side, the neutrinos coming in from the left. You can see it interacts and produces this sort of quite low-density number of particles. And then on the top, there's a much higher energy, much more kind of interacting particle. And this is an electron. This is a real classic signature of an electron interacting with material. And this is just the same thing, but looking straight in. So if the neutrino was coming straight into the board, then it would look like, well, it did look like this. And so by analysing this special emulsion detector, we're actually then also able to make the first ever electron neutrino observation of electron neutrino produced from a collider as well. And So now we've seen the muon neutrinos, we've seen the electron neutrinos. You can also see muon neutrinos in the emulsion, but it's not quite so exciting because it's a much simpler thing, but it's still easy to extract. And so this, I hope you agree, has been really a success for a very short amount. This is only using 1 year of data so far, and in principle the Large Hadron Collider will run until the 2040s. So our spokesperson, one of our spokespeople, has joked before that all previous collider experiments that cost of the order of $1 billion observed 0 neutrino events. And with FASER, with a cost of around $1-2 million, we've seen over 100. So hopefully I've convinced you of proof of principle, this thing is good value for money. Okay, so that's it really for the neutrinos. The last, I've got 2 more things I want to talk about briefly. One is about searching for dark matter. So as some of you may be aware, what we see, what we know about in the universe only accounts for about 5% of all of the stuff in the universe, depending on how exactly you define stuff. And 25% of the rest of the stuff is dark matter. And we have good reasons to believe that dark matter is a particle-like in nature, but we've never seen that particle. And there are lots of well-motivated ways of looking for it. So this is the iceberg visualization of the matter, dark matter, and dark energy distribution in the universe. This is the cake representation, which a friend of mine actually baked. So if you go on Twitter or X or whatever it's called now and you look for physics cakes, you can also find out more wonderful creations like this. And so we have this evidence that the rotation of galaxies is faster than you expect if you just base it on the amount of matter that you can see. It implies there's something there that's not reflecting anything and not, even absorbing any light. It doesn't really interact with light at all, and so it's why it's called dark matter. We have other evidence for it as well. So this is an amazing simulation of essentially the density of objects at a very large scale in the universe. And you can see there are these kind of tendrils, these bits in connecting different areas of different density. And you can simulate this and you can compare it to how it looks from astrophysical measurements, and it only matches if you have some dark matter content in there. So there's this body of evidence for it. But then there's different ways that you can look for dark matter. So on this plot here, I have the mass of the new particle that you're looking for, the dark matter particle, and on the y-axis, the coupling, the probability of it interacting with anything. And so at the top right, you have the strongly interacting and heavy particles, and on the bottom left, you have the weakly interacting and light particles. And traditional searches, like at Atlas, are looking in this top right bit, but actually, there are properties that you need to match for something to be a good dark matter candidate, and to do that, everything has to be on this straight line, so it doesn't have to be up here where the traditional searches have been at particle colliders. It can be down here in the very light and very weakly interacting area. And very weakly interacting also implies very long lifetime. So you might have seen on a few places I talk about long-lived particles. So you can have a particle that has such a long lifetime that it's produced in Atlas, then it travels the 480 meters to FASER, and only then does it actually decay into anything. Does it change into other particles? And so what you can do is, in quite a similar way to the neutrino measurements, you look for the appearance of a particle. So this A prime here is a dark matter candidate. It again will leave no signal in these green boxes where we're looking to make sure that we only see the appearance of something, not just something that's come from further upstream. And then you see that it can decay most of the time into an electron and a positron pair. This leaves a very distinct signature in the detector of 2 tracks that are separating because of the magnets. And then you have the calorimeter, and you have a very high energy deposit in the calorimeter. What did I call it earlier? The energy measurer or something. And so you can look for these, and you don't need to know the details of these graphs, but just to show that they are with increasingly strict requirements on what we think the signal will look like. So The black dots are the data, and you can see to begin with there's loads of them. The red, green and the blue are what a dark matter candidate would look like. And you can see that if we apply some of our criteria to get rid of all of the background, you still have some data left. But if we only look in this region up here, you already don't see any data. And then in the end, we actually apply even more tight requirements to make sure that we really don't have any backgrounds. And now you definitely don't have any data in the signal region. And so this means we did not discover. So we did observe the first neutrinos produced from a collider. We definitely did not find dark matter yet. You might have heard about it before now if we had. But it is a really good proof of principle that we can try and do this. So this thing here is just telling you the regions that you were sensitive to, which is inside the blue line. The red line is particles that would be very good dark matter candidates. And if you remember the different colours and what they did, the one thing that's kind of cool about this is that we're like the first time that anybody's looked in this region. Okay, it's not a huge chunk of this region, but it's not all of the data. It's the first time anybody's looked here since the 1990s, so 30 plus years of no progress looking for these things. And we've now proved that you can do this kind of very low background, look for exotic particles appearing in your detector kind of search. There are other types of particle that you could look for. I'm not going to go into that. Okay, I'm nearly done. The last thing I want to say a couple of words about is what's next. So here is a bird's eye view of that bit of Geneva, where Atlas is this blob in the middle. And right now, where FASER lives is in this little green box, and you can see this red dashed line as the direct line towards FASER. We put this thing in a disused tunnel, using borrowed bits of kit from other experiments, spending as little money as possible, and you can only fit a certain size detector even in that tunnel, so it was very constrained from the beginning. But now there's the proof of principle to do this. We're looking at building a dedicated facility, and this thing would be called the forward physics facility. So everything very much in line with the beams is called backwards and forwards, and so we just call this forwards. And it would be a purpose-built, dedicated experiment with its own shaft, its own cavern, enough space to put a whole bunch of similar but complementary experiments in there. These things are already in the relatively far on stages of R&D. This is roughly what they would all look like underground, all put together. And they have a real interesting physics program, so there's things to do with like looking for these sterile neutrinos that you can do even better. You can look for quarks, such a weird name for a particle, lots of other weird and wonderful exotic particles. And there's this huge physics program that we can do at the Forward Physics Facility. In the UK, we're actually leading the R&D development on the upgrade to FASER that would live in this facility that's imaginatively called FASER 2. And so I and colleagues here and elsewhere in the UK are working on this. And this is the projection that I showed you before of all of the measurements that you can get out of FASER as it is currently after another 2 years of taking data. And this is what you can do with the same setup at the FPF, and you see that the uncertainties on these measurements are so small that you basically can't see them, and that's just because you get thousands more neutrinos coming through. You can say stuff about sterile neutrinos just by measuring the energy distribution of these neutrinos, all sorts of stuff. You can also vastly improve how sensitive you are to dark matter, so the darker yellow here is what FASER is expected to be able to do in the next couple of years, and then if you built FASER 2 it would be significantly better, and depending on what type of dark matter particle you're looking for, it's even more better than that. And then finally, it also can help teach us a lot about the proton. So the decrease of these different coloured bands essentially corresponds to better understanding of the proton, and that can even then feed back into the Atlas physics program, for example, and making more precise measurements there. Okay, so that's me basically done. So just to summarise, so we had the first direct observation of muon neutrinos from a collider back in March, and then over the summer, the same thing with electron neutrinos. This was, without any hint of modesty, called The Dawn of Collider Neutrino Physics by this American Physical Society, which is kind of nice, if a little bit over the top. We are setting the first limits on the possibility of dark matter that we can detect at these places, proving this very low background kind of technology for the first time and looking at in a new region of these phase spaces for the first time in 30 years. And we're trying to do something better to take us through to the end of the 2040s when the LHC will finally stop running. So possibly coming to a particle collider near you in 2028. That's it. Thank you.
Oh yeah, thank you very much, Josh. That was really, really interesting. I'm sure everyone would agree. Does anyone have any questions at all? I knew you were very quick.
What does it?
Well, the ones that we use in FASER are extremely simple. So what it does is it has a you have to force the object let's say it's an electron. You have to force it to interact and then shower. There's like an electromagnetic shower that you get when a high energy electron goes into the calorimeter. You need a very high density material to do that. Like, so we have layers of lead in there that start the shower, and then interleaves with layers of a scintillating detector. So a detector where when particles go through it, it emits light. And basically the amount of light is proportional to the amount of energy, and you just measure it like that. And it's low tech.
But basically you measure kinetic energy. Neutrino gave those electrons.
Yeah, so in the case of an electron neutrino, it would produce an electron. That thing can fly through the detector, and then you can measure the energy of that electron in the calorimeter. With the muon, it's more difficult because the muon doesn't really interact with the calorimeter, so there you have to do something else. You can measure the momentum using the tracking detectors instead. But yeah, that's the general idea.
Anyone else? Middle of the room.
Why
because they come from a much more commonly produced particle in those forward regions here. So they're produced by, oh no, hang on. This one. So they're produced by a particle called a kaon, and there's lots of them, and they, most of the time, well, a large fraction of the time, decay to muon neutrinos. And that's just not because of weird helicity things and stuff. It's not the case for electron neutrinos, so they preferentially produce a lot more muon neutrinos.
most beautiful rainbow colour. There's different colours.
It's time information, basically. So it's not strictly time. It really is distance, but you kind of think of it as time. So it's they're basically saying as you get further away, these are coherent periods in time, or distance if you assume the thing's travelling at the same speed. And yeah, they more or less just correspond to different layers in the detector.
How do you distinguish from
Yeah, so we have a background estimate for the background coming from no beam in the LHC. So what you can do is you can say, okay, I've got, most of the time I'm expecting to get all of my neutrinos from the collisions in Atlas, and those are the ones that I actually care about. Then you can run your data analysis for all of the time where there are no collisions in the LHC and there are no collisions in Atlas. you see how that looks, and then from that you can determine whether you have to worry about that as a background or not. And it turns out that we're sufficiently deep, so it's only about 80 meters, but 80 to 100 meters underground, that and because they're not traveling horizontally enough to look like our signature, it's essentially a negligible background. It turns out we don't have to worry about it at all.
Yeah, just like.
So, well, that's a very good question. So we, you see, oh no, so I'm looking at the wrong page. So in the data that we're taking now, which will still go on for about 2 more years, we only expect to see 4 of these tau neutrinos. So, I mean, if you've got 0 background or nearly 0 background and you see 4, that can be observation of tau neutrinos. But it is just really, really difficult. And that is actually one of many things that motivates this larger, more complicated facility, the forward physics facility, because there you get enough of these that you can really start doing interesting measurements, not just saying we saw them or not. You can really try and measure the properties. It's a similar reason for why the muon neutrinos are much more common than the electron neutrinos. They're just the mechanism by which they have to be produced is different. That's mainly because they're a lot heavier. So they're really, so not the neutrinos aren't heavier. The tau lepton that the tau neutrinos come from is much, much heavier. And so it's harder to produce in collisions, just have a lower probability of getting them.
That was a very eager hand.
Yeah. The dark Higgs is my favourite. So, the Higgs boson is, let's have a look at this one. So this figure here is all about looking for the dark Higgs. Because the Higgs is the most recently discovered fundamental particle and, is the target of a lot of research by these big collaborations like Atlas. Despite that, it's still one of the least well understood. And for instance, one thing that is very hard to do is to measure how often a Higgs decays to different things. What's the total rate at which it decays to different things? It's very hard to measure that. And what that basically means is that you can, there's room for there to be new particles that a Higgs boson can decay into. And one of those is a dark Higgs. And it comes up in the same sort of the mechanism for introducing it theoretically is quite similar to this one, which is a dark photon, where you basically have a type of field that is in a different, it's called the dark sector. So it's in a slightly different kind of space in quantum field theory to the usual standard model fields, and therefore it's harder. It's got a weaker interaction because it has to come in a slightly different way. But nonetheless, it can come in, and it can come in at a rate where you can see it, and that's what you look for here, basically. So it's the dark Higgs version of a dark photon. I'm not sure that's a very good explanation. So we can just about look for them already with the current setup. The reason why it's harder is because the Higgs boson, one of the main features of it is that it has a higher likelihood of interacting with heavier particles. That's like the way that it gives all these particles mass. And so the dark Higgs inherits that from it. So a dark Higgs is much more likely to be produced from the decay of a heavier particle than it is from a lighter one. And these heavier ones end up because they have more mass, they give a bit more of a bump to their decay products. So they go at a wider angle. And so that means that if you've only got a detector that's 20 centimeters around and you bump it out a bit, by the time you get 500 meters away, it's out quite a lot and you don't see these things anymore. But if you can make the detector 3 meters wide instead of 20 centimeters wide, then you capture these back in, and that's why you get much, much better sensitivity. So the real way to do this is with a bigger purpose-built experiment.
Wonderful. I think, I was going to say one more question, but now it's 7. How eager are you? Yeah, Josh. Last question.
So FASER is not really optimized at all because it basically goes where this tunnel happens to be. I told you it was kind of cheap and cheerful. What we did do is, you know, you saw in that figure I had where we put where all of the neutrino candidates are, and then there was the red cross that told you where the middle of really the line coming out of Atlas would be. You could see that was not quite in the center, and that's because we already dug down about 0.5 meter into the floor of this tunnel to try and get as close to this direct line from Atlas as we could. But then if you go more than that, it's really like civil engineering problems. You get past the existing concrete and then everything becomes more expensive to do. And so we went as low as we could, as close as we could. And we also make the detector slightly movable. So you can really, if you put it in slightly the wrong place, you can shift it over a bit to try and be as close to this direct line from Atlas as you can. But otherwise, it's not particularly optimized, which is another reason why the dedicated facility is really good, because then you can re-optimize that basically.
Yeah, well, let's thank Josh again. Yeah, and then I have to pay my advertising dues. So in 2 weeks' time, am I right in that? Yeah, 20th of November we have the next Sussex University talk, which is going to be an engineering talk on is waste heat a wasted opportunity? I can tell you no more about that talk. We will find out when that talk rolls around. But yeah, thank you for coming again. See you soon.